ETAP is a widely used software for power system analysis, including voltage drop calculations. Voltage drop refers to the reduction in voltage that occurs as electrical current flows through conductors in a circuit. This reduction is due to the impedance of the conductors. Accurate voltage drop calculations are essential for ensuring the proper operation of electrical equipment and systems. If the voltage at the load is too low, equipment may not function correctly, leading to performance issues or even damage. Several standards govern voltage drop calculations, with IEEE standards being prominent in North America. These standards provide guidelines and methodologies for calculating voltage drop under various operating conditions. ETAP, as a power system analysis software, incorporates these standards into its calculations, ensuring compliance and accuracy. The validation and verification, often abbreviated as V&VE, process is crucial to confirm that the software performs as intended and that the results are reliable. Validation focuses on whether the software produces the correct results for a given set of inputs, and verification ensures that the software is built correctly, adhering to the specified requirements and design. In the context of ETAP, validation and verification against IEEE standards involves comparing the software's voltage drop calculations with benchmark results obtained using manual calculations or other validated tools. This process confirms that ETAP accurately implements the equations and methodologies specified in the IEEE standards. The specific IEEE standards relevant to voltage drop calculations include IEEE 141, also known as the Recommended Practice for Electric Power Distribution and Coordination of Industrial and Commercial Power Systems, commonly referred to as the Red Book. This standard provides guidance on various aspects of power system design, including voltage drop considerations. It outlines acceptable voltage drop limits for different types of loads and provides methods for calculating voltage drop in various circuit configurations. Another relevant standard is IEEE 399, also known as the Recommended Practice for Power Systems Analysis, the Brown Book, which covers a wide range of power system analysis techniques, including load flow studies, short circuit analysis, and voltage drop calculations. This standard provides detailed information on the modeling of power system components and the application of different analysis methods. ETAP's validation and verification process also involves testing the software's ability to handle different types of loads, conductor sizes, and circuit configurations. This includes simulating various scenarios, such as motor starting, transformer inrush, and imbalanced loading conditions to ensure that the software accurately predicts the voltage drop under these conditions. The validation process typically involves comparing ETAP's results with hand calculations or results obtained from other validated software tools. This comparison helps to identify any discrepancies or errors in the software's calculations. If any discrepancies are found, the software developers investigate the cause and implement corrective measures. Once the software has been validated, it is important to verify that the software is built correctly, adhering to the specified requirements and design. This involves reviewing the software's code, testing its functionality, and ensuring that it meets the specified performance criteria. The verification process also includes checking the software's documentation to ensure that it is accurate and complete. The validation and verification process is an ongoing process that is repeated whenever the software is updated or modified. This ensures that the software continues to perform as intended and that the results remain reliable. ETAP's validation and verification against IEEE standards provides confidence in the accuracy and reliability of the software's voltage drop calculations. This is essential for ensuring the proper operation of electrical equipment and systems. Accurate voltage drop calculations can help to prevent equipment malfunction, improve system efficiency, and enhance overall system performance. When performing voltage drop calculations, it is important to consider several factors, including the conductor size, length, and material, the load current, and the power factor. The conductor size should be selected to minimize voltage drop while also meeting the ampacity requirements of the circuit. The conductor length should be kept as short as possible to reduce voltage drop. The conductor material should be chosen to provide low resistance. The load current should be accurately determined to ensure that the voltage drop calculations are accurate. The power factor should be considered because it affects the amount of current that flows through the conductors. A low power factor can increase the voltage drop in a circuit. To further clarify, consider specific examples. For instance, suppose a 120-volt circuit supplies a load of 20 amps through a 100-foot long run of number 12 American wire gauge copper wire. Using a voltage drop calculator or appropriate tables, one can determine the voltage drop. The resistance of number 12 copper wire is approximately 1.98 ohms per 1000 feet. Therefore, for a 100-foot run, the resistance would be 0.198 ohms. The voltage drop is then calculated using Ohm's law. Voltage drop equals current times resistance, which in this case is 20 amps times 0.198 ohms, resulting in a voltage drop of 3.96 volts. The percentage voltage drop is calculated as voltage drop divided by the source voltage, multiplied by 100, which is 3.96 volts divided by 120 volts, multiplied by 100, resulting in 3.3%. This value is generally acceptable as it falls within the typical recommended limit of 5% for branch circuits. However, if the load was increased to 30 amps, the voltage drop would increase to 5.94 volts, and the percentage voltage drop would increase to 4.95%, getting closer to the acceptable limit. If the run length was increased to 200 feet with the same 20 amps load, the resistance would double to 0.396 ohms, resulting in a voltage drop of 7.92 volts and a percentage voltage drop of 6.6%. This exceeds the recommended limit of 5%, indicating that a larger conductor size may be necessary to reduce the voltage drop. Now let's consider a 240-volt circuit supplying a motor with a load of 40 amps through a 250-foot run of number 8 American wire gauge copper wire. The resistance of number 8 copper wire is approximately 0.778 ohms per 1000 feet. For a 250-foot run, the resistance would be 0.1945 ohms. The voltage drop is 40 amps times 0.1945 ohms, resulting in a voltage drop of 7.78 volts. The percentage voltage drop is 7.78 volts divided by 240 volts, multiplied by 100, resulting in 3.24%. This is within the acceptable limit. However, if the motor has a low power factor, for example, 0.8, the current would effectively increase. The voltage drop would also increase. To compensate for voltage drop, one can implement several strategies. Firstly, increase the conductor size. Using a larger conductor reduces the resistance per unit length, thereby reducing the voltage drop. Secondly, shorten the circuit length. Shorter conductor runs inherently have less resistance and thus less voltage drop. Thirdly, improve the power factor. Installing power factor correction capacitors at the load can improve the power factor, reducing the current drawn from the source and minimizing voltage drop. Fourthly, increase the supply voltage. If feasible, increasing the supply voltage can reduce the percentage voltage drop. However, this may require adjustments to equipment and must be done in accordance with applicable codes and standards. It is also useful to note that National Electrical Code, or NEC, provides guidelines and regulations for electrical installations, including voltage drop considerations. In EC Section 210.19, A1 Informational Note Number 4 recommends that the voltage drop on branch circuits should not exceed 3%, and the combined voltage drop on feeders and branch circuits should not exceed 5%. In EC Section 215.2, A3 Informational Note Number 2 provides similar recommendations for feeders. These recommendations are not mandatory requirements but are intended to provide guidance for designing electrical systems that provide adequate voltage at the load. The actual voltage drop limits may vary depending on the application and the requirements of the equipment being supplied. It is important to consult the manufacturer's specifications and applicable codes and standards to determine the appropriate voltage drop limits for a specific installation. Using ETAP to model these scenarios allows engineers to quickly and accurately assess voltage drop under various conditions, ensuring that electrical systems are designed to operate within acceptable voltage limits. Remember to consult with a qualified electrical engineer or electrician for specific design and installation requirements. The information provided here is for general educational purposes only and should not be considered a substitute for professional advice.